Many thanks for coming to the History of Science seminar series here at the Institute for Advanced Study. As always, I wanted to thank the person who provided the funds, our director, Robert Dykoff, who's in the back. Thank you for providing the funds for this series. Just as a quick announcement, next lecture will be here next week at this time, as those of us who grew up with Batman, same bat time, same bat channel. It will be Julia Frommer from the Johns Hopkins University, who will be speaking on Robokan is Zazen, Psychology in Buddhism and Mori Masahiro's Robotics. So that will be this time next week. As I mentioned last time, to kick off the series, my goal is to invite outstanding scholars in the history of science working on projects relevant to the types of scholarship that being done by the natural scientists and mathematicians here at IAS. And with that in mind, it's an honor and a pleasure to introduce today's speaker, Stephanie Dick, who joined the Faculty of History of Sociology of Science at the University of Pennsylvania in the fall of 2017. Before that, she was a junior fellow at the Harvard Society of Fellows after completing her PhD in the history of science from Harvard. She works on history of computing and mathematics, particularly in 20th century America, as we'll hear today. Her first book project explores early attempts to automate proof and new formulations of mathematical reasoning and knowledge. The book offers a historical answer to the question, what is thinking if a computer can do it? By way of an answer, she recovers and reconstructs how different communities theorized human cognitive faculties with automation in mind. She's also working on the history of New York State Identification and Intelligence System, which was one of the first efforts to introduce computing to American law enforcement and to mobilize automated recognition systems for faces, license plates, and fingerprints for policing. She's published on the history of Microsoft Windows, in particularly one of its most infamous failures as a window, pun intended, into the experience of modern computing. And she's also working on a book-length study of how computer science became an academic discipline. I just also want to briefly announce that part of my other goal, other than bringing really exciting scholars who are working on subjects near and dear to IAS, is to increase the collaboration with the History of Science group at Princeton, and I thank the Princetonians for coming to my talk today. I just also want to announce that Sophia will be giving a talk. Sophia will give a talk at Princeton tomorrow at 4:30 p.m. in 211 Dickinson Hall. It's a different talk than this is. It's a true doubleheader. It's called Making Up Minds, which will be a different lecture. So you're cordially invited to attend that. Now is a good time to turn off your cell phones, in case you have cell phones on. Without further ado, please welcome Stephanie. Thank you, Stephanie.
That's yours. I think that's yours. Thank you so much, Miles. It's really an honor and a pleasure to be here. I've sort of exhausted the list of historical sites that have featured in my historical research as sites that I have also had the honor to visit, with the exception of this one. It's played such an important part in the history of computing, and it's actually an honor and kind of an exciting pleasure to be here and to have an opportunity to share some work with you all in this context and in this way. So today I'm going to be talking a little bit about mathematical proofs, which of course are one of the many things that mathematicians are interested in constructing, circulating, understanding, unpacking. Proofs, of course, are meant to establish that something is the case in mathematics, that a given mathematical object has a certain set of properties, or that it behaves in a certain way, or that it has a given relationship to something else. And perhaps more importantly than that, proofs are meant to generalize, to establish that that property holds not just for some finite set of cases, but always and everywhere. So we want to prove that the sum of the angles inside a triangle is 180 degrees, not just for this triangle or that one, or even for all of the triangles that have ever been constructed, but for all possible triangles that can be constructed always and everywhere, or at least always and everywhere within Euclidean geometry. But in spite of this claim to time and placelessness, mathematical proof also has a history. Different kinds of demonstrations serve to convince different communities that something is true or not. The standards of demonstration to which different mathematical communities adhere are not always the same. And in that sense, mathematical proof, so often held up as our most sort of objective and ahistorical way of knowing has also been really controversial throughout its history. So there have been times and places when diagrams have been a central tenet of the way that mathematical demonstrations are produced. There are other times and places where diagrams are categorically rejected as dangerously attached to spatial intuition and therefore risky as tools for cultivating mathematical thought and knowledge. Sometimes in places you can make certain assumptions, you can use certain inference principles, and elsewhere these are rejected. Different kinds of demonstrations count as proofs for different communities, and a large part of what the history of mathematics has become in the last several decades is an attempt to recover and reconstruct what counts as a proof to whom and why in different moments from the history of mathematics. And I've been really interested and have been working on this project for the last decade or so that circulates a question about whether or not computers might become theorem provers. Whether computers are capable of producing the sorts of demonstrations that will convince mathematicians that something is true in mathematics. So beginning in the 1950s in the United States, different communities set out to see whether they could get a computer to produce something that looked like a rigorous proof or a proof of something in mathematics. And I've been interested in everything that happened since. So as you might expect, and as in many domains, computers made possible some new and really exciting possibilities for mathematical proof because they can be so efficient at rule following, so efficient and accurate at carrying out the kinds of rule-bound explorations that we so often associate with mathematics. But computer proofs, as probably some of you know, have also been quite controversial. Some of them, like the infamous computer-assisted proof of the four-color theorem, are so long that no person could ever read them all the way through. To convince herself, sort of line by line, that the proof is correct and understand what it's made of and what it's showing us. Other computer proofs make use of operations that are so combinatorially complex that they're sort of hard to follow, hard to unpack, hard to understand. And some people have argued that maybe these kinds of computer demonstrations shouldn't count as proofs at all, or that maybe at best they could show us that something is true, but not why, which is the more important question for many mathematicians. And for a historian of science, this has been a fascinating debate, of course. But my work has been motivated by a conviction that in order to make sense of the epistemological significance of introducing computers to mathematics, we have to actually also ask a prior question. Instead of just looking at the demonstrations that computers produce, I wanted to know how were those computer proofs made and made possible in the first place. This is a prior question about what was actually involved on the ground in getting computers to produce these demonstrations that philosophers and mathematicians would then argue about. What made this possible? What kind of work was involved? What kind of problem solving? What new ways of thinking or adapting mathematical ideas to machinery had to be worked out in order to design and implement the computer programs that would produce these proofs? What did that look like as a technical problem, a political problem, an institutional problem? And so in order to understand this prior question and see what the epistemological stakes of automation in the first place were, I've been working on an early history of a field that's called automated theorem proving. And the people working within this field are doing just what you would expect. They are trying to automate different parts of mathematical proof or mathematical problem solving, and it's a fantastic field to study historically because beyond that, the people working within it disagreed about basically everything else. They disagreed about the character of human mathematical faculties, like reasoning, like knowledge, like intuition. They disagreed about whether some version of those might be reproduced in a machine. They disagreed about the limitations and possibilities of computers, what kinds of tools they might turn out to be. They disagreed also about what proofs ought to look like, whether they should be just logically sound and very, very long, or understandable and readable to a human mathematician. And to give you sort of a sense of what the field looks like, here are some snippets of the almost always anthropomorphic language that the people I study used to describe in the post-war period what kind of agency they believed computers would have in mathematics. So at one end of this spectrum, at the top here, are those people who believed that at least in principle, much of what human mathematicians do could ultimately be automated, and that computers would eventually become like colleagues or coworkers or mentors. Then there are those slightly less optimistic people who imagined the computer would be more like an apprentice or a graduate student. Sorry guys, capable of making some contributions to the field, but not without a lot of expert guidance, and that maybe the significance of that work would be limited. And at the other end of the spectrum were those who believed that actually the only kind of contribution machines or computers might be able to make were to the very menial and mechanical parts of mathematical work, and used the language of assistants and slaves and servitude to describe the kinds of contributions that their computing systems were meant to make. So part of the project that I've been working on is to recover where these different ideas about what kind of tool the computer is sort of came from in the first place. But more importantly, I'm interested in how the people I study built these ideas about mathematical labor and about computers and mathematics into the programs that they wrote. I wanted to know, what does it look like to implement an assistant, or to implement a colleague or a coworker, or what does a program that's a graduate student, what does that look like? And in that sense, my work is somewhat new, or trying to do something different than a lot of the history of computing that's come before me and on which I depend utterly. For a very long time, the history of computing was a history of computers, the machines themselves. And beyond that, there are histories of the very important thinkers and corporations and institutions that gave shape and character to early computing regimes in the United States and elsewhere. Insofar as the history of software has been written, it's largely been written at the level of sort of the algorithm or the code. Here is, lots of media theorists are interested in the program as a list of sort of symbols, and what can we make of that? I'm interested instead in the practice of making software. How do people actually make things run? And especially in the 1950s on machines that have 52 kilobytes of memory, what does that look like as a practice? So I'm focused on implementation, not on algorithm, not on code, but on the labor that goes into making computer programs that will run on a machine. And what I like about this focus is that it opens up the history of software to the archives. Implementation, the traces of all of the hand-drawn simulations, the diagramming practices, the tried and failed attempts to sort of interpret printouts from your program. That's an archival source base that I have been very keen to incorporate as the bedrock of my project. And it opens up software as a practice instead of the sort of abstract counterpart to hardware, which is how software is so often fashioned. So for me, it's all about what were they actually doing? How did they make these programs run? And that's been the sort of motivating feature of my work until now. So within the field of automated theorem proving, there were roughly two approaches that I'm interested in the book. And they amount to two theories of what constitutes the ability of human beings to sort of solve problems or prove theorems in a particular way. One branch of this field goes by the name of automated reasoning, and they believed, people working within this field, that what really matters for human intelligence in mathematical theorem proving or problem solving is our reasoning faculty. For them, the whole game was trying to identify what does human reasoning consist in, or what is reasoning, what are the rules of reasoning, and can they be translated into a set of programming rules? That's the sort of goal of this field. The other sort of approach to this says our intelligence and problem-solving capacity does not derive from our ability to reason or to think a certain way. It's totally dependent on what we know. knowledge, expert knowledge, is the bedrock of expert problem solving in any domain, whether it's math or medicine or chemistry. And so for them, they wanted to identify what does mathematical knowledge consist in and how can it be encoded such that it might be automated. So those are the sort of two approaches to this problem that I've been interested in sort of studying over the years. And what I want to do with the rest of my time today is introduce a very early and very famous example of an attempt to identify what kinds of rules constitute human reasoning that led to the development of the logic theory machine in the mid-1950s at the Rand Corporation in Santa Monica, California. I then want to talk about different reactions to that effort to automate human reasoning that sort of put in the middle of them a question about what reasoning is in the first place. All these people seeking to automate reasoning disagreed about what reasoning was, or what it looked like, or how it could be automated. So I want to talk a little bit about the debate that circulated around the very idea of reasoning in the wake of this sort of very important program from the 50s. And then I want to talk about this a very important early system within the expert systems tradition, who abjectly rejected the idea that the automation of reasoning alone would lead to powerful theorem-proving or mathematical problem-solving systems, and instead said what we need to do is codify mathematical knowledge more than reasoning, such that it can be put to work in a sort of theorem-proving or mathematical problem-solving way in the form of the MACSYMA system, whose development began in the 1960s at MIT. It actually still exists in some way today. It's the predecessor to things like Wolfram's Mathematica or Maple, these algebraic systems that were sort of beginning development at that time. So first I'll start with a case of automated reasoning. And it orbits around these canonical texts in modern mathematical logic, Principia Mathematica, that were written by two British mathematicians, Alfred North Whitehead and Bertrand Russell, around the turn of the 20th century. And Russell and Whitehead, many of you do not need to hear this story, but I will repeat it for the sake of the rest. They were working within a community of logicians who at the time believed famously that all of our mathematical knowledge, so every theorem from every branch of mathematics, could and should ultimately be proved within one standardized logical formalism. So they, in this text, lay out a set of premises and a set of inference principles, 4 of them in particular, or 5, depending on how you count, that they believe are all that you need to construct on a firm and deductive bedrock the truths of mathematics. That everything we know in mathematics could ultimately be derived by applying those inference rules to those premises or axioms and sort of building up our mathematical knowledge in that way. It's a notoriously cumbersome system to work in. They managed to prove that 1 + 1 is equal to 2 on page 283 of volume 1, just to give you some sense of that. But that was the goal. It was a formalist vision of mathematical knowledge that suffers irreparable sort of constraints later in the 20th century, but that is a subject for another story. But much less remarked upon about these volumes is the fact that Russell and Whitehead were also committed to coming up with a particular way of writing mathematics on the page, a symbol system that they believe would equip the heads and hands of mathematicians to reason in the requisite way to sort of work within their formal system. This was for them a material project as much as it was a formal project, that you had to learn to work with this symbol system in order to think in the right way. For them, reasoning was tied to a set of material practices. They put it like this in the first edition intro: the symbolic form of the work has been forced upon us by necessity. Without its help, we should have been unable to perform the requisite reasoning. It has been developed as the result of actual practice and is not an excrescence introduced for the mere purpose of exposition. No symbol has been introduced except on the grounds of its practical utility for the immediate purposes of our reasoning. So for them, reasoning meant to do a kind of inferential work within a formal system, and they thought you needed a particular set of material tools to do it. So it's a formal project, it's also a material project their symbol system was meant as much as possible. I find it actually very difficult to work with, so there's an irony in that. But they meant to make patterns easy to see, to make abstract things like logical relationships more accessible, and also to piggyback on people's familiarity with certain kinds of algebraic expressions that they assumed readers would be used to. So Principia represented this combined formal and material project, and my question was, what happened in the 1950s when somebody tried to automate the proofs of the theorems from those volumes? The logic theory machine was built to prove theorems from Principia Mathematica, and I wanted to know what happens to the way inference is being conceived, to the way that logical propositions are being represented and manipulated, to the way that logic is being understood in the transition from the paper and book materiality of the Principia project to the magnetic drum storage of the Joniac mainframe computer named after your own John von Neumann and developed in the image of the IAS machine in the 1950s when these guys sought to automate this formal system. So the logic theory machine was designed by these two men. Alan Newell actually abandoned a PhD program in mathematics at Princeton in 1950 to take up a permanent position at the RAND Corporation in Santa Monica, California. Herbert Simon was at the time a professor of business administration at the Carnegie Technical Institute, soon to become Carnegie Mellon, and he started consulting for RAND in 1952. And the two of them got together and were coordinating on projects like how do we optimize the training of radar operators at Air Force bases. RAND was an Air Force-funded sort of defense establishment think tank tasked with the job of trying to figure out how to build good strategies for future global wars. And one of the main approaches to this sort of rather large and amorphous task that developed at the RAND Corporation was called systems engineering, which said, if we can't know what future wars are going to look like, what countries they'll be between, what weapons will be involved, what technologies will be available, how do we study how to win and strategize in the future? And they came up with this idea that maybe you could look at systems formally and try to figure out how different kinds of systems work at a formal level and mathematize them and find ways to optimize their performance so that you could plug in whatever people, whatever countries, whatever technologies, and hope that you have some generalizable tools. So for these RAND people, everything was a system. The Bolshevik government was a system, the railway was a system, the agriculture of the Midwest was a system, the weapons on a plane were a system, and they wanted to study the formal properties of these systems and look for ways to optimize their behavior in hopes that that would be useful for whatever came in the future of warfare. So it may seem very odd that in the 1950s, these guys who are worried about training radar operators and thinking about nuclear war through the lens of system engineering are also interested in automating the proof of logical propositions from a turn of the 20th century text. Why were they doing that? The answer famously, of course, is that Newell and Simon came to believe that both modern digital computers and human minds were also systems. And more importantly than that, that they were the same kind of system. Simon called them species of the same genus. And that genus was information processing systems. Both minds and digital computers, for them, took symbolic information as input, manipulated it according to a set of rules in order to make decisions, formulate opinions, formulate judgments, solve problems, and that if you could identify what constituted the human mind's information processing apparatus, you could translate that into a computer program, and in so doing, reproduce or simulate that behavior in a computer program as well. And the logic theory machine was their first attempt to actually make a program that performed some kind of human problem-solving capacity. So it was an empirical exercise in producing human-like problem-solving behavior in a computer, and for them, it was part and parcel with this bigger systems engineering research program that they were so invested in at RAND. But in order to do this, the first thing they needed, of course, was some model or some account of what it is that human mathematicians do when they solve logical problems or prove logical theorems, such that they might be able to translate it into a set of rules for automation. And for that, they turned to a Hungarian mathematician by the name of George Polya, with whom Alan Newell had studied very closely as an undergraduate at Stanford University some years prior. And Polya was deeply invested in the project of mathematics pedagogy. And he believed that contrary to what Russell and Whitehead have in mind, mathematicians don't actually just deduce things. In practice, mathematicians don't just apply inference principles to axioms in hopes of eventually deriving sort of interesting theorems. Polya thought instead mathematicians do all kinds of things. They look for counterexamples. They work backwards from things that they already believe to be true. They look for analogous problems. They look for counterexamples. They build models. They sort of play around. Mathematical practice, according to Polya, was a lot richer than these sort of fictions of us as deductive machines might imply. So he wrote, I always love this, certainly let us learn proving, let us learn to deduce things from axioms, but also let us learn guessing. And he called these ways for guessing, these tricks of the trade that mathematicians actually deploy in practice, heuristics, from the Greek for to find. It's like a navigational term. But more than this, Polya did not believe that the tricks of the trade that mathematicians learn and deploy were somehow esoteric and inarticulatable. He believed they could be identified, they could be formalized also as rules, and then taught to students to make them better at doing mathematics. He called them the rules of plausible inference instead of sort of certain inference, certainty being the guarantee only of these formal logical systems. So this was sort of exactly what Newell and Simon wanted. This was a rule-bound model of what human mathematicians do in practice, according to this one particular mathematician. So they set out to try to automate and formalize as rules this vision of human mathematical reasoning. And the logic theory machine had two heuristics in particular. The first was working backwards. The logic theory machine did not begin from the premises of Principia Mathematica and deduce things, hoping to eventually deduce propositions or theorems from the books. This, of course, would also lead to an exponential explosion of data and had been ruled out as a possibility earlier in the 50s anyway. Instead, the logic theory machine worked backwards from known propositions in Principia using a method they called subproblem chaining. So it would start with something it wanted to prove, and then the logic theory machine would do a sort of deductive reverse engineering, where it would generate a set of subproblems that, if they were true, would lead to the desired conclusion in sort of one permissible inference step. And then it would produce a second set of subproblems that, if true, would lead to those subproblems, and so on and so forth, in hopes that eventually the axioms themselves, or the axioms and some set of already proved theorems, would be produced as subproblems. And if that happened, you could just run that path backwards, and you would have a really nice deductive proof of the thing you wanted to prove. Of course, they also proved there was no guarantee that this method would work, and it provably fails, actually, on some subset of propositions from Principia, but that was fine for them because they thought, like, mathematicians also have no guarantee that the path that they're on is going to lead them to the desired conclusion either. So this was the model of the logic theory, of sort of human reasoning that informed the logic theory machine. And this is the description that is usually given of the program as well. But models don't run. Models themselves don't run on computers. I wanted to know, how did they get this thing into a program that could run on the Joniac computer, which did, in fact, have 52 kilobytes of memory at the time, sort of mind-blowing. And very tellingly, neither Newell nor Simon themselves had the experience with computing machinery to do the implementation work on their own, and had to enlist a third collaborator, a much less famous guy by the name of John Clifford Shaw, He trained as an engineer and served in the Air Force during the war, and then took a position at the RAND Corporation in the numerical analysis department after the war. Tellingly, the numerical analysis department became the programming department eventually, and they were the team of people who implemented all of the calculations, the models, the simulations that people elsewhere at the RAND Corporation were interested in running. They worked in the basement, which was the only space large enough to house the machinery of the time. John Clifford Shaw described it himself as a sweatshop later in his life. The machines at this time were sort of noisy. They emitted a lot of heat. They often worked without shirts on. There was a sort of physical component to the work of carrying these boxes of punch cards back and forth between tabulating machines and sort of computing machines. And they were the ones who had a kind of intimacy with the machinery and asked the question, how do I take this model of reasoning and actually make it run on this computer? And this is the kind of work that's always really fascinated me about the history of software in general, is how do you take our ideas and interface them and rethink them through the affordances and the limitations and the possibilities of our computing machinery. Simon had very little to do with this part, actually. He sort of reported that all the work was done in the summer of 1955 once they'd come up with the model, because for him, the material substrata just didn't matter. What mattered for him was this abstract, formal level. It could be brains, it could be a computer, it could be a mix of humans and computers. As long as it could sort of follow these rules in some way, it didn't matter. But Newell and Shaw had to deal with the material reality of the Johnniac. And thankfully, they were actually living in different places at the time, so their experimentation has been all recorded in correspondence that lives between the two of their archives. And one of the biggest problems for them was actually also Whitehead and Russell's problem. They wanted to know, how can we represent or encode logical propositions in Johnniac's memory such that we could manipulate them in the way we have to do this kind of subproblem chaining and working backwards. And they experiment by hand with a lot of different possibilities for encoding logical propositions. And in the end, they land on the linked list information structure, or known to us as the linked list data structure. Data structures or information structures are exactly what they sound like. They're just ways of structuring data in computer memory so as to be controllable, useful, meaningful encodings of the myriad sorts of things that we would like to put into the computer. There are many different kinds. The linked list was one of the first. It's also completely prolific. I encountered linked lists, 15 years ago when I started programming, and it was really wonderful to discover that they in fact had an origin at all, and that the origin was here at the advent of automated theorem proving as a way of encoding logical propositions. And in a linked list encoding, each element of a logical proposition gets encoded by a set of 6 alphabetic values that indicated what kind of element it was, what position it holds in the proposition, whether it's negated, is it a variable or an operator or whatever. And that information, those values, are stored in a set of contiguous bits in Johnniac's memory. And the last set of bits here labeled Q stores the numerical address in Johnniac's memory of the next element in the proposition that can be stored anywhere else in Johnniac's memory. So here the goal was not to make, anything visible like patterns or structure. It was just to economize for sort of computing memory. So the only way that logical propositions exist as a unit in this encoded form is processually. You have to go through all these different address pointers from one element to the next. Logical propositions become dynamic in this encoding. You can see them thinking differently about what logical propositions are in order to imagine them as these processual and discrete kind of dynamic artifacts that will live in computer memory. And the motivation for doing this was just to economize for one particular kind of problem, which is that there was such limited memory. So to give you an example, if you wanted to delete an element from a logical proposition in this encoding, all the computer would have to do is take the address pointer from the previous element and reroute it to point to the address of the next element in computer memory, and then you would add this deleted element to a running list of memory that was currently available. So that's 2 operations instead of n operations, where n is the length of the proposition, and that's in the best case scenario where you don't have to also create memory that could hold the proposition. This was all about economizing for this kind of memory management. And when you start to look, this is what the history of computing is all about. It is about experiments in economizing for the limited resources of computing machinery. And people have to rethink what medical diagnoses consist in, what logical propositions are, anything you wanted to compute about in the 50s and 60s. You had to reimagine in a way that accommodated the limitations of the machinery. And I think this comes with new ways of thinking about what these objects are. It's maybe, so in these sort of encodings, I do think that even though at some sort of formal level they're the same objects, there's a sort of different set of behaviors and properties that come through in this automated form. And it's maybe more obvious in the way that the inference principles of logical deduction were also translated. So the 4 or 5 sort of principles of inference that are laid out in Principia Mathematica that are meant to be self-evident to us, to require no further explanation, to be obvious and atomic of our own thinking, are here translated into 44 variations of 8 list processing operations. Things like assign and branch, or calculate, or store, or test in different ways. The sort of self-evidence of reasoning that was meant to be encoded in the inference rules of Principia become these very alien operations that accommodate this new computer-oriented encoding that was designed to service the logic theory machine. So even here, in a case where Newell and Simon are desperately seeking to preserve human thinking, to preserve what human reasoning consists in, to make a machine manipulate symbolic information in the same way that we do, they have to reinvent what those operations look like, introduce new symbolic alphabets, new sort of broken down ways of thinking about what inference is that can be executed by the sorts of things that the Johnniac can do. And that sort of retooling or reimagining of what inference is anyway through the lens of the limitations of the machine is, I think, or should be, I think, a part of the story about what happens epistemologically when we introduce computers into mathematics. So just to sort of summarize this part of the story, this was an attempt to automate human reasoning. This was an attempt to identify what human mathematicians do and automate it as a rule-bound sort of processes. And in the midst of that, through the lens of sort of Randian systems engineering, they come to see human reasoning as a form of rule-bound information processing. And then they adopt a particular model of mathematical reasoning from Polya that sort of breaks down problem solving into a kind of rule-bound formal heuristic practice, which they then seek to automate. And that's their model of human thinking that they want to preserve across into the machine. But when that model meets the machine and its really sort of strict constraints, they are still motivated to think in a new way about what inference is and what logical propositions are, and they translate them both. The propositions become these linked list dynamic processual data structures, and inference principles become these operations for manipulating linked lists. And that, I propose, is a kind of transformation in the idea of what is sort of behind these tools. And it was kind of controversial. It was also very successful in some, according to a particular metric. So it proves, I think, 38 of the first sort of 90 canonical theorems in Principia. Sir Bertrand Russell was still alive at this time and has a nice little correspondence with Herbert Simon in which he says, A, don't tell the school kids that we can automate this stuff, and B, if I had known that a computer could do this, maybe we wouldn't have spent a decade of our lives doing it by hand. And he also concedes that one of the proofs that the logic theory machine produced was more elegant than the one that he and Whitehead had published. Famously, also, this program was the only running program presented at the 1956 Summer Conference or Workshop at Dartmouth, around which ideas about early artificial intelligence coalesced. So this heuristic approach to theorizing human reasoning became very popular amongst that community. So people were looking for the heuristics of medical diagnosis, the heuristics of organic chemistry, the heuristics of whatever you name it, so such that they could be automated amongst early artificial intelligence practitioners. But there were also those who thought, this is not what it claims to be. And so I'll say just a little bit about ways that reasoning as a faculty were being sort of contested or negotiated in the wake of this particular program. So one of my favorite, also one of the more vocal critics of the logic theory machine was this man, Hao Wang. He was a Chinese-American logician. If you're interested in him, he will be a major player in the talk I'm giving tomorrow, but I'll be able to say tragically little about him today. But he looked at the logic theory machine and said, Newell and Simon have made a fundamental error. They mistook the machine for being like the human mind because they believed a fiction that had been cultivated by logicians. He put it this way. He says, logicians had worked with the fiction of man as a persistent and unimaginative beast who can only follow rules, and then the fiction found its incarnation in the machine. And so he thought the Russells and Whiteheads of the world who imagined that human reasoning was in any obvious or simple way a rule-bound exercise were sort of oversimplifying and spinning a tale about us. And Newell and Simon mistakenly looked at the computer and said, it's just like us because it resembled the fiction rather than the reality. And in some ways I'll discuss at length tomorrow, Wang, who was at the time a sort of secret Marxist, who was very influenced by more material visions of sort of both knowledge and social life, went so far as to say that a particular act of recognition or reasoning depends on one's genes, the history of one's mind and body, some essential relation to desire, even race, class, sex, and many other factors, where Newell and Simon wanted to produce a fully formalizable and abstract idea of human reasoning. Wang wanted to insist that human reasoning was historical, it was embodied, it was social, and that whatever they were automating, it wasn't human reasoning. And he goes further to say, and actually even if computers were like us, it would still be a mistake to use them to do the things that we can already do. And Wang was way more interested in cordoning off human reasoning as something human and way more complicated than you might imagine, and saying we should capitalize on the fact that these machines are so different from us, that all they are is rule followers, which we have never only been. So he describes it like this. He says, the human inability to command precisely any great mass of details sets an intrinsic limitation on the kind of thing that is done in mathematics and the manner in which it is done. The superiority of machines in this respect indicates that machines, while following the broad outlines of paths drawn up by man, might yield surprising new results by making many new turns which man is not accustomed to taking. We are, in fact, faced with a challenge to devise methods of buying originality with plodding now that we are in possession of slaves which are such persistent plodders. So I have a lot to say about this passage, but you'll have to stay tuned until tomorrow to hear more about it. But for him, the promise of machines for mathematics was not that they were like us, but that they were fundamentally unlike us, and that they might better embody the vision that logicians have already always had of their project of reducing sort of mathematical reasoning to this rule-bound set of processes. So that was one reaction to this attempt to automate human reasoning, was nope, that's not reasoning. Reasoning is something we do, and we don't really understand it, and it's complicated, and maybe it's not rule-bound, but we can make use of machines because they are not doing that. A different sort of imagining of reasoning came from this man, John Allen Robinson, who was a classicist by training. He got interested in computing, in part by spending summers consulting at Argonne, another sort of defense-funded think tank institution just outside of Chicago. And Robinson thought that it was precisely also because of the power of machines that we might now have an opportunity to rethink reason itself. And through his training in classics and later logic, he decided that our logics have always been constrained because they were tethered to what human minds can do. And that with the possibilities of computing came the option of breaking open what reasoning is at all by reinventing what logic is without human understanding or human psychology at the heart of it. So he puts it like this. He says, traditionally, a single step in deduction has been required for pragmatic and psychological reasons to be simple enough, broadly speaking, to be apprehended as correct by a human being in a single intellectual act. When the agent carrying out the application of an inference principle is a modern machine, the traditional limitation on the complexity of inference principles is no longer very appropriate. More powerful principles, involving perhaps a much greater amount of combinatorial information processing for a single application, become a possibility. So Robinson thought, why is it that all our logics have as inference principles things that are obviously true to us? We might be able to imagine all kinds of logically sound inference principles that are not obvious to us. And he proposed the development of what he called computer-oriented logics that were reasoning in the sense of being about inference principles, but in which the inference principles were not supposed to be immediately obvious or accessible or self-evident to a human mind. And he proposes his own, in that same paper, the resolution principle, which just very generally, given two parent clauses that contain what are called complementary literals. So if one contains P, the other would contain its complement, which is not P. With a single application of the resolution principle, you can resolve those parent clauses into a child clause that has no instance of P or not P at all. So it's sort of a way of simplifying by removing particular literals by this kind of resolving principle. But to give you a sort of heuristic example of how this works, this is the kind of thing that Robinson thinks has been the heart of logic for most of its history. These sort of principles that are meant to be obvious to anyone. So like the syllogism, which is one of our oldest, Socrates is a man, all men are mortal, therefore Socrates is mortal. This is supposed to require no further explanation or justification to some human cognizer. Resolution allows you to do things like this instead. So from the premises, all hounds howl at night, anyone who has cats will not have any mice, light sleepers do not have anything which howls at night, John has either a cat or a hound. You can resolve, sort of removing these complementary literals, that if John is a light sleeper, then John does not have any mice. So this is a perfectly sound inference. He goes to great lengths to prove that it is a sound inference principle. It also actually turns out to be the only principle you need to prove, I think, everything in Principia. So it's a powerful, efficient resolution or inference principle, but it has forfeit human understanding. We cannot follow proofs that are constructed with applications or iterations of resolution, and that was the whole point for Robinson, was that our understanding, steps that accommodate our psychology, has actually been holding back reasoning, holding back logic, holding back mathematics. And yes. Oh, I mean, it's just not, this is a simple baby problem from like an undergraduate class to give you a sense of how this works. But if you imagine that these propositions, here, like these x's can all be logical propositions unto themselves. These things can expand to be sort of unreadably long unto themselves, these parent clauses, and then they can get resolved very simply. And you can follow the proof. The proof is like 9 pages. But this isn't in the same way as a syllogism, meant to be a self-evident, in need of no further explanation, sort of atomic unit of human thinking. And it's only the beginning. Resolution is what really makes this field of automated reasoning take off. So variations on resolution, resolution provers that interact with other resolution principles become the sort of most powerful automated theorem-proving systems in the field. There are conferences and journals and associations and awards and competitions that get started around this idea that we should design logic not to accommodate us, but to capitalize on the kind of combinatorial work that computers can do. So in the wake of the logic theory machine, this whole really fascinating conversation unfolds about what people think reasoning is. There's the school of Newell, Simon, Shaw, and also others who want to automate human reasoning. But in so doing, they have to rethink it in some ways that are kind of alien and unfamiliar in order to be able to accommodate the machines on which they seek to automate these practices. From people like Wang, and there are others, there's this rejection that that's what reasoning is. They want to cordon off reasoning as some uniquely human faculty that we don't understand at best, and at worst isn't rule-bound at all. And that's something that people do, and we should just exploit the plotting character of machines to make new things possible for mathematics. And then there are people like Robinson and much of the community that starts with this automated reasoning goal, who want to actually expand what we mean by logic and come up with new rules of inference that are perfectly logically sound, but that are not designed to be self-evident or obvious in a single intellectual act, as it were, in the way that Robinson described. And this field is alive and well. I go to their conferences. Resolution is alive and well. Although in 2012, Robinson himself gave a talk at the Conference on Automated Deduction in Manchester and flagged this move as a potential mistake, saying that maybe we shouldn't have been quite so quick to jettison human understanding from our efforts in automated theorem proving for various reasons that I'll also say more about tomorrow if you're going to be around. So to finish now, I want to talk a little bit about an effort in this other approach to the introduction of mathematics or of computing to mathematics, this expert systems approach. So for them, it's not a conversation about reasoning at all. It shouldn't be about identifying the rules of reasoning, whether human or machine-oriented, because that isn't really what our problem-solving capacity consists in the first place. Instead, we should be trying to figure out what mathematicians know and finding ways to encode that for automation. So Edward Feigenbaum, who was one of the founders of computer science at Stanford, also sort of early practitioner of expert systems and AI, described it this way in 1977 as a critique of the kind of artificial intelligence that Newell and Simon were interested in. We must hypothesize from our experience to date that the problem-solving power exhibited in an intelligent agent's performance is primarily a consequence of the specialist's knowledge employed by the agent, and only very secondarily related to the generality and power of the inference method employed. Our agents must be knowledge-rich, even if they are methods poor. So according to Feigenbaum, automated reasoning practitioners were just having the wrong conversation as they tried to figure out what the right rules were for doing a certain kind of problem solving. They wanted instead to try to figure out what people know and how to encode it for automation. And because he's here, I should say I learned a lot about expert systems from Mikey McGovern, who wrote a wonderful thesis as an undergraduate about expert systems in biology. And I was there to see it, and it was awesome. So for these guys, there's this fundamental rejection of what historians of science might call tacit knowledge. The idea that there are things that people know that they cannot say, or that cannot be formalized or made explicit. Feigenbaum writes that much of expert knowledge is private to the expert, not because he's unwilling to share it publicly how he performs, but because he is unable. He knows more than he is aware of knowing. But we have also learned that this private knowledge can be uncovered by the careful, painstaking analysis of a second party. So within expert systems is this practice called knowledge engineering, in which expert systems practitioners pick the right baby problems and the right interview questions through which they truly believed that they could distill and elicit and make explicit anything that an expert knows. And there's some, I think, sort of terrifying hubris in this project, as we'll see as it plays out for mathematics. So I'll just finish by saying a bit about the MACSYMA system, for the Project Mac Symbolic manipulator. Project Mac was the sort of body that housed computing research at MIT before the creations of the labs and later EECS. And MACSYMA was the first sort of large-scale, nationally distributed, so-called algebraic or symbolic computing system. And it was designed to assist mathematical problem solving and theorem proving. So it could integrate sometimes, it could multiply matrices, it could do Fourier transforms, it could do a lot of different kinds of algebraic simplification, sort of manipulating algebraic expressions from one form to another to help in different kinds of problem solving. And the idea for them was that we should try to consolidate and encode everything that mathematicians know so that it's available as a kind of library of ready-made automated operations that physicists and mathematicians and engineers, all connected to the ARPANET, can use by dialing up our PDP-10 computer. And they may not need to know these things themselves, just know when certain operations are useful so that they can dial in and put them to work in their problem-solving practice. So they too also needed a theory of what they thought mathematical knowledge consisted in. And they described it like this in some of their early documentation. A rough hypothesis is that a mathematician knows perhaps 10,000 mathematical facts. For example, if a student learned 4 facts an hour, 4 hours a day, 5 days a week, 9 months a year, as I'm sure many of you have done, he would learn some 12,000 facts. The average mathematician may not be able to sustain this pace with complete retention, but he has been learning for a longer time period. So if this is starting to look a little bit suspicious to the mathematicians in the room, I think that's right. It's a profoundly reductive idea about what mathematical knowledge or any knowledge consists in. I sat in on a conference in last May of a group of expert systems practitioners who are still alive, recounting their memories, and they still talk about knowledge in this way. You know, people described doing knowledge engineering with a doctor, and I sat down and I talked to him, for 4 hours, and at the end I held up a list of 200 facts, and I said, this is what you know. And so there is this sort of engineering optimism, both that knowledge can be elicited, but also that it can be formalized as these sort of lists of facts. It's a very modular theory of knowledge, unlike artificial intelligence systems that have a set of sort of top-down rules that get applied everywhere. Here, the idea is that you've got some pattern matching, and that's one set of rules unto itself, and you've got limits, and that's another set of rules. You've got simplification, that's a different set of rules, and you can just call on these different modules independently of one another, and there's no reasoning apparatus, no logical control that holds them all together and makes them examples or instances of the same thing. So it's a modular theory of knowledge. It's also an operational or a procedural vision of knowledge. You have to be able to translate what you know into an instruction in order to encode it or automate it in this way. Michael Genezareth, who was one of the developers and troubleshooters at Harvard and MIT in the 70s, he wrote it, it's a conception of mathematical knowledge as a body of programming rules. And this was one of the things that made the system hard to use, is that mathematicians define things and think about objects in ways that are not processual at all, or not operational at all. So just a very baby example. This is a perfectly good definition of an even number. N is even if and only if there exists a number m such that n is equal to 2m. It's a perfectly good definition of evenness, but it does not contain an explicit procedure for creating even numbers or for checking if a given number is even either. We could make one, divide n by 2. If there is no remainder, then n is even. That's an operational or procedural definition of evenness. But mathematicians often don't work with definitions like that. So encoding things in MACSYMA and using the MACSYMA system required them to start thinking processually about what they were doing. And this, according to Genezareth, was one of the hardest things about using the system, was that it required mathematicians to reimagine the objects in which they were interested in these procedural or programmable ways that accommodated the machine. It also required that they become planners. This is a schematic of what they called Satan, which was a certain kind of strategic planning that they imagined MACSYMA users would have to adopt, in which they took the problem they wanted to solve and broke it down into a pathway that charted through the capabilities of the MACSYMA system. So mathematicians here had to become planners of a certain kind embody a particular way of thinking that took them through the system. But the hardest problem for using the MACSYMA system actually related to this question about what algebraic simplification was anyway, because that's what the system was used for most readily. So all the time, mathematicians and physicists take equations of a certain form and translate them into a different form because it helps them understand something or intuit something in a better way, or it's easier to work with. And I don't know about you, but for me, I would prefer to work with the top equation rather than the bottom one. Although these are equivalent, they'll output the same result for whatever the value of theta. And this may seem counterintuitive, but for the developers of the MACSYMA system, this may in fact have been the simpler representation. The reason being, we all are happy to track between the 6 different trigonometric functions whenever it's most convenient. For the developers, for the same reasons as the linked list has the form it does, it was more economical to implement just one and to force everyone to do everything in terms of cosine. And that was not so intuitive or useful for users. So this was a description that Joel Moses, who headed up the MACSYMA program for a long time, gave. Simplification is the most pervasive process in algebraic manipulation. It is also the most controversial. Much of the controversy is due to the difference between the desires of a user and those of a system designer. The user wants expressions which he can comprehend, which usually means that the expressions presented to the user should be small. The designer wants expressions that can be manipulated with great ease and efficiency. And this led to a whole host of problems for users where they had to be trained to think like developers in order to work with representational schemes that may not have been as intuitive. And this was one of the big problems that they had to deal with. And so in what I think is a great twist, because these people totally rejected the idea of tacit knowledge, they still ran right into it in the sense that they had to try to find a way to train people to think this way and to train people to use this system at a distance, and spent so much of their time writing and rewriting primers and advisors and manuals. The main manual came out sometimes every few months in a new version, just trying to get people to think in such a way that they could make use of the system. Moses said, books will still be used once MACSYMA has been completed, but only for tutorial exposition. And they got their wish, of course, as tutorial writers, and eventually they concede the lesson that all historians of science know, which is that knowledge transfers best face-to-face rather than formalized on the page, and they founded their users' conferences in 1977. So to summarize this story, for them, they're interested in encoding human knowledge as the grounding for our ability to solve problems, but they also rethink what our knowledge is. It's modular. It's not governed by any one reasoning system. It has to be procedural, and this was difficult. And whatever freedom we imagined was afforded by a system like this came only as the result of a lot of discipline to think a certain way, plan a certain way, problem solve in a certain way. And here, too, we see that our knowledge becomes kind of unfamiliar as it's translated into forms that accommodated the machine. So the book, these are the themes I come back to all the time. You can't automate anything without transforming it, without rethinking it, without accommodating it to the affordances of the machine. There's also this sense lingering behind all these stories of a new kind of economy of proof. Proof gets divided up and the labor gets spread between people and machines in different ways. There's all these concerns about optimizing for certain kinds of resources. Reasoning and knowledge, which are the pillars of this field, are also moving targets in this history as they get reimagined and translated in all these different ways. And then always through this story, these human faculties that are meant to be automated or at the heart of automation sort of take on these unfamiliar qualities as they interface with the machinery. And I talked too long, so I will stop there. Thank you so much for your time.